In exercise 234, we start to see how drawing resonance structures will allow us to see places where there is slight charge, and that charge ends up being the stickiness of the molecule. Where you have charges, that's where that molecule is going to tend to stick to other molecules that have the opposite charge. So if you just look at this molecule right here, it doesn't seem at first blush like there would be any charge at all. Maybe if you used the rules from chapter 1, you'd say, okay, oxygen's really electronegative, so it pulls the electrons to itself, becomes slightly negative, and the carbon is slightly positive. And that would be about it. So the only slightly positive thing you would have predicted in chapter 1 would be this carbon here. But as we'll see, when we draw the resonance structures, there are going to be many more positive charges besides just that. So we'll go through the 5 resonance patterns for this molecule, and then we'll just draw in the slight positive charge into the molecule, and that'll be the whole answer. All right, so do we have an allylic lone pair? Well, the first thing you want to do is draw in the lone pairs. We have 2 lone pairs on the oxygen, none on the carbons because no carbon has a negative charge, and 2 on the oxygen so that it has a total of 8. So we do have lone pairs, but these lone pairs are on an atom in a double bond. They're not one atom away, so they're not allylic. How about an allylic positive charge? We don't have a positive charge at all. How about a lone pair adjacent to a positive charge? No positive charge at all. How about a pi bond between atoms of differing electronegativity? We do have that. That second bond between the carbon and the oxygen is a pi bond. Oxygen is way more electronegative than carbon, and so that's a pi bond between 2 atoms of differing electronegativity. So we definitely have resonance. And so we want to draw those big billboard error brackets that advertise to people that all the molecules inside, those are not going to be, no individual molecule inside is a true molecule. The true molecule is the average of all of them. So we'll draw our molecule in there. We've got that 6-membered ring. And then we have a double bond to an oxygen here, and a couple more double bonds here. Okay, well we said we have that 4th pattern, a pi bond between 2 atoms of differing electronegativity, and the curved arrow pattern for that is that the pi electrons go onto the more electronegative atom. And so we'll draw a resonance arrow telling us to average the structures. And so that gives us our next structure to work with. Okay, so anywhere where you have the tail of a curved arrow, those are electrons that are moving away from there. So you erase those. Anywhere where you have the head of a curved arrow, those are electrons that are arriving there, so you draw those in. If the head of a curved arrow points at an atom, then you draw those in, as a lone pair. So we're going to have a lone pair here. And the way the formal charges would change here, if you calculated them, is this oxygen now has a negative charge, and the carbon here has a positive charge. Okay, so that's our first resonance structure. We are still on this first one. Do we have the 5th pattern, a compound or conjugate with conjugated pi bonds in a ring? We do actually have that. We do have those conjugated pi bonds in a ring here. We will worry about that pattern in a second. That pattern is going to reappear throughout all of these resonance structures. And remember, all that pattern does is it switches the placement of the single and the double bonds in that ring. So right now we'll make a mental note. Whatever drawings we have, we would duplicate those drawings just with the double and single bonds switched. But for now, let's focus on the positive charges, because notice when this happens, you don't change the formal charge on any of those carbons. And here we're looking for changes in charge. So we'll keep that in the back of our mind that that is there, but we're not going to take time and space to draw that in right now. Okay, So now let's look at the second structure. Is there an allylic lone pair there? Well, there is. There's this allylic lone pair. These allylic lone pairs. Oh no, forgive me. Those are not allylic lone pairs because if you go just one atom over, you are not at an atom in a double bond. So if you go one atom over from where the lone pairs are. Okay, so we don't have that first pattern. Sorry about that. How about an allylic positive charge? We do have that. This positive charge right here, if you go one atom over, you're at an atom in a double bond, so that positive charge is allylic. And so you could draw a curved arrow. The pattern for this, when you have an allylic positive charge, the curved arrow pattern is that the pi electrons go to form a new pi bond toward the positive charge. So anywhere where you have the tail of a curved arrow, you erase electrons. Anywhere where you have the head of a curved arrow, you draw them in. If the head of a curved arrow is pointing at a bond, then you draw those in as a bond. And if you calculate the formal charges, you would see that there would be a positive 1 formal charge here. Now I'm not drawing in the hydrogens, because we've done so much practice with that in previous problems. But if you're having trouble getting these same formal charges that I'm drawing, then what you'll want to do is to go back to the previous problems, make sure you feel comfortable with drawing in hydrogens, and do that with this molecule. So when you copy the molecule, you have all the hydrogens drawn in, so it's easier for you to calculate the formal charges. Okay, so that's our next resonance structure. Now, the purpose of this exercise is for us to see where there is positive charge in the molecule. So we want to see how this positive charge can move around. We don't necessarily have to draw all of the resonance structures that are possible. We want to draw the ones that have a positive charge in them at different places. So we were looking at this other structure there. If we go to the third pattern, it doesn't have a lone pair adjacent to a positive charge. We don't have a pi bond between atoms of differing electronegativity. All the pi bonds here are between carbons, which have the same electronegativity. And we do have that conjugated pi bond in a ring, as we said, but that's not going to affect the positive charges, which are what we're really looking for here. So that's the one resonance structure for this second molecule that would affect the placement of a positive charge. So that's the one we're going to draw in here. All right, so now we're on this third molecule. We want to see if there are any resonance structures that will change the position of that positive charge. And we could, if we were drawing all the resonance structures, you'd want to go through all of these, and you could do that and draw every single resonance structure. But the ones that change the position of a positive charge are the second and the third. You could create a positive charge with the fourth. So we'll go through those. Technically, this structure now does have an allylic lone pair. All of the lone pairs on that oxygen are one atom away from an atom in a double bond. But if you do the curved arrows for those, the electrons come down, that forms a lone pair. You get a negative charge, but you don't get a positive charge anywhere. You don't move around positive charge, and that's really what we're interested in this exercise. So we're not drawing all of the resonance structures, just the ones that show the movement of the positive charge here. So although we do have this pattern and it would give us another resonance structure, it doesn't involve the positive charges, so we'll go on to the next one just for the sake of time and space. So for this allylic positive charge, we do have that. This positive charge here is actually allylic in two places. It's allylic to this carbon and it's allylic to the other one. If it interacts with the one on the left, on the right, that would bring us back to our structure here. We get a new structure if it interacts with the other pi bond. So we draw these, copy that in. And what ends up happening here is that pi bond moves over, and you have a new positive charge on this carbon. So I'm going to move a little faster in terms of describing how electrons move using the curved arrows because we've done so much practice with it, in the same way that I'm moving faster in terms of writing in the formal charges because we've also done so much practice with that. Okay, so let's see if this new structure, or I should say, we went through that second pattern. We should check out the third and the fourth patterns. In this third structure, we don't have a lone pair, an extra positive charge, and we also don't have a pi bond between atoms of differing electronegativity. So we're good with all of the patterns of this molecule that change the position of the positive charge. All right, now let's go through the patterns here that would change the position of the positive charge. So the allylic lone pair, we do have that pattern, right, just like we had it before, just that would not move or create any positive charges. So although technically there is another resonance structure here we could draw, it wouldn't help us to identify where the positive charges are, so we don't have to draw it in this problem, just because of what this problem is asking for. So we'd go on to the second one. Do we have an allylic positive charge? And we do. That positive charge there is allylic to two positions. It's allylic to the right and to the left. Now, if it interacts with the pi bond on the right, then you end up with the previous structure you had. So we've already drawn that, so we'll have it interact with the pi bond on the left. Oops. So the pattern for this is that the pi electrons go toward the positive charge. So we copy that. Oops. Thanks. Sorry. We copy that and then paste it in. And for this structure, what we'd do is we would move these pi electrons here. They would go to form a new pi bond. That would get rid of this positive charge and create a new positive charge on this carbon here. Okay, so we're looking at this structure. We saw it has an allylic positive charge. We took that into account. It does not have a lone pair adjacent to a positive charge, and it doesn't have a pi bond between two atoms of differing electronegativity. So we've drawn all the ways that this molecule could move a positive charge. Okay, how about this next one? And what you'll notice is from here on out, all of these resonance structures are only going to have allylic positive charges. They also do technically have the allylic lone pairs, but like we said before, those won't be creating or moving the positive charges that we are interested in this problem. So we don't have to draw the resonance structures for those for this problem. And so we'll notice we won't have either of those two. And like we said with the fifth one, that also doesn't move or create positive charges. So we're just going to be dealing with this allylic lone pair. And what ends up happening is that it moves around the molecule. So those pi electrons move over, become a new pi bond. That means this no longer has that positive charge. It's right here. So we can continue drawing these. So that's now allylic again. So we could take this structure can move those electrons over. If you do that, this pi bond moves over and you don't have this positive charge anymore. It moves over here. And you'll notice you have yet another allylic lone pair there. So we can take that structure, draw it here. We're going to move these pi electrons toward the positive charge. So those electrons move. Those electrons move to go somewhere else. The place where they go is over here. That means that we don't have this positive charge anymore there. Instead, we have it on this carbon. And notice that that is actually a duplicate, right? That puts the positive charge on a carbon that we've seen before. So we actually have reached the end of the line. Once any other place where you try to move that positive charge using the pattern of the allylic positive charge, any place where you try to move it already exists in a resonance structure that we've already drawn. So all of the resonance structures, not for the compound, because we didn't draw a lot of them, but all the resonance structures that show the placement of positive charge are contained in those brackets right there. And so notice, the true molecule does not look like any of these. The true molecule looks like the average of all of them. So what would the true molecule look like? It would look something like this. Notice, all these bonds are somewhere in between single and double. All of these bonds are somewhere between single and double. There is a slight negative charge on the oxygen. And now let's look where the positive carbons were. The carbon attached to the oxygen. Now it's not going to have a full positive charge because there are other resonance structures that have zero, so it'll be slightly positive. If you go 2 carbons over, there's a positive charge. It won't be a full positive charge on the real molecule because there are other structures where it's 0, so it'll be slightly positive there. 2 more over, we have another positive charge. It won't be a full positive charge because we have a bunch of other structures where it's 0, so slightly positive. Next, 2 more over, slightly positive, slightly positive, slightly positive. Notice at the top, bottom left, bottom right. There are other structures where it's not a full positive charge, so it's all, when you average them all out, it's just a partial positive charge. So if you take, so those are all the areas in the whole molecule where there is a slight positive charge. There are a lot of them. And if you looked at this original molecule, you would never guess, ever, that a negatively charged molecule would be attracted to that carbon there. But when you draw the resonance structures, you can see that there is a resonance structure that has a positive charge there. So when you average them all, there is a slight positive charge on that carbon. And so when you put that negative species in a beaker together with this, it's going to try to attack all of these slightly positive places. Now, one molecule will only be able to attack one, but if you put 1 trillion molecules in the beaker there, they're going to try to attack every single one of those places. So, just for emphasis, I'll put dots on the slightly positive carbons. that's how you can use resonance to sort of see how charge that's not explicitly drawn in could still be there when you redraw the resonance patterns.